Most people drive every single day without realizing they're riding on top of one of the toughest, most precisely engineered structures in the modern world. Roads look ordinary, just flat gray strips stretching toward the horizon. But the truth is far stranger. Beneath that simple surface is a hidden world of machinery, physics, chemistry, and construction techniques so advanced that even some engineers are surprised by what goes into the making of a modern concrete highway. Roads aren't just poured. They're engineered like long, horizontal buildings designed to survive decades of brutal weather, crushing truckloads, and millions of wheels grinding across them non-stop. And here's the part nobody expects. The United States builds over 40,000 kilometers of new roads every year. And a massive portion of them are made from concrete that's designed to last nearly half a century. But how do engineers turn raw stone, sand, steel, and cement into those rock-solid structures you drive over every day? How do they make a surface that can handle everything from blazing heat to 20-ton trucks without falling apart? What you're about to see is the side of road construction most people never imagine. The precision, the massive machines, the strange chemical recipes, and the global differences that make each country's highways completely unique. And by the end, you'll never look at a road the same way again. Every year, the US quietly builds enough new roads to circle the entire planet, not once, but more than once. It's one of those huge national projects that continues in the background, 24/7, without most people noticing. And here's where things get even more surprising. Nearly 1/3 of the federal highway system is built using concrete instead of asphalt. If you've ever wondered why so many major American highways have that pale, rigid surface instead of the softer black look of asphalt, there's a reason. Concrete lasts longer. A lot longer. A well-engineered concrete pavement can survive 30 to 40 years with only minimal maintenance. Asphalt rarely reaches that without major repair work. Concrete also tolerates heat in a way asphalt struggles with, which is why highways in hotter states, Texas, Arizona, Nevada, rely heavily on it. When the sun beats down at 40 degrees Celsius, asphalt can soften and deform, especially under heavy truck traffic. Concrete doesn't care. It shrugs off temperatures that would turn asphalt into a sticky mess. And trucks are the real reason concrete wins. Heavy freight traffic puts enormous stress on road surfaces. Asphalt bends and flexes. Concrete resists. So for major interstate highways designed to carry endless streams of semi-trailers, concrete is often the smarter choice. It costs more upfront, but it pays off over decades. But even with all those advantages, the secret isn't the concrete itself. It's everything that happens before the first drop of it touches the ground. Because before concrete is poured, the entire world beneath the pavement must be prepared with a level of precision and strength that rivals skyscraper foundations. And that's where the story truly begins. Every strong road starts with the ground beneath it, and that part of construction is far more intense than it looks. Before anything is built, engineers head out to the proposed route and start studying the land like detectives. They dig test pits, drill cores, measure soil strength, check for soft spots, and analyze how the earth will react under long-term loads. If the soil is weak or unstable, the road will eventually crack, sink, or warp. So this early stage is where future failures get prevented. They also figure out the exact amount of earth that must be added or removed. Maybe the terrain is uneven. Maybe a curve needs widening. Maybe the land dips too much and needs to be raised with compacted layers. Every detail matters because even a few centimeters of uneven elevation could throw the entire project off. Then there's the environmental side, drainage paths, nearby water sources, and how construction might impact surrounding areas. A road isn't just a line on the map. It's an entire ecosystem change, and engineers must account for every ripple effect. Once the route is confirmed and plans are finalized, the construction crew starts clearing the land. Vegetation gets removed, the topsoil is stripped away. Heavy machinery begins shaping the rough foundation that will eventually carry thousands of tons of concrete. And this is where precision takes over. The soil must be compacted to the point where it behaves like rock. A grader smooths the area, shaving or lifting the earth by millimeters at a time. Underground utilities, power, drainage, water conduits are installed. If the road doesn't have sidewalks, drainage ditches may be dug along both sides to prevent water from pooling under the final pavement. But the real magic is in the compaction. Giant rollers press layer after layer of soil until it reaches the density required to support the future road. Too soft and cracks appear years later. Too dry and the soil crumbles. Too wet and it turns to mud. To avoid all that, water trucks drive ahead of the rollers, spraying just enough moisture to create the ideal binding conditions. Everything is monitored constantly. Laser surveying equipment ensures the surface matches the design exactly. Sensors measure vibration levels and compaction depth. Field technicians walk alongside with handheld devices checking density. Even before a single ounce of concrete is poured, the groundwork resembles a carefully calibrated industrial process. And once this massive invisible structure is finally ready, the part everyone recognizes, the concrete, can finally begin. If you've never seen a slipform paver in action, imagine a huge metal creature crawling slowly forward, swallowing concrete from one end while leaving a perfectly shaped highway behind it. These machines are enormous. Some stretch more than 20 meters long. They look like industrial assembly robots on tracks, except they're operating outdoors, rolling over massive construction zones. But before the paver arrives, crews prepare the base layer with an incredible level of accuracy. Huge dump trucks pour out tons of crushed stone. Bulldozers spread it across the prepared soil. And rollers again and again press it into a solid foundation. Depending on the project, this stone layer may have multiple levels, a thick bottom layer for strength, and a finer top layer to provide a perfectly even surface. To the untrained eye, this seems simple, but perfect compaction is one of the hardest parts of road building. Every meter must be equally firm. No soft spots, no pockets of loose stone, no variations in thickness. To hit these standards, technicians use vibrating rollers, pressure sensors, and laser systems that constantly check the surface as the machines move. After days of preparation, sometimes up to 4 days for long segments, the base is finally ready. And that's when the star of the show rolls in, the slipform paver. This machine does almost everything. Spreads the concrete, levels it, compacts it, vibrates it, and shapes it into the final form. Think of it as a giant printer creating a concrete highway in real time. But the machine is only as good as the concrete it receives, and that concrete is created through one of the most controlled industrial processes in construction. Concrete might look like simple gray sludge, but its recipe is engineered down to the kilogram. Every batch begins at an industrial mixing plant where raw materials arrive by truck or conveyor. The aggregates, the stones, sand, and gravel, are stored in huge silos or compartments, each holding a different size and type. Keeping them separate is crucial because the mix must be precise. Wheel loaders scoop the aggregates into the feeders. Calibrated belt scales weigh each type with remarkable accuracy. A batch might require exactly 200 kilograms of one stone size, 800 kilograms of another, and 500 kilograms of fine sand. Every ingredient is measured according to a preset design that engineers developed earlier, based on local climate, expected traffic, and required strength. Water is measured just as carefully. Too much and the concrete becomes weak. Too little and it becomes unworkable. The water is stored in tanks, controlled by sensors, and released into the mixer either through freefall or high-pressure spray depending on the plant's setup. Then come the chemical admixtures, the secret weapons of modern concrete. Superplasticizers for workability, accelerators for cold climates, retarders for slow drying, anti-cracking agents. These chemicals can dramatically change the behavior of concrete and must be measured with almost laboratory-level precision. Once the ingredients enter the mixers, whether it's a twin-shaft high-speed unit or a heavy-duty pan mixer, everything blends at high speed for a set cycle time. The result is a uniform, perfectly engineered mixture ready for transport. But this is where the clock starts ticking. Concrete only stays usable for about 60 to 120 minutes before it begins to harden. So as soon as a batch is ready, the mixing drum of the truck starts rotating and the vehicle speeds toward the construction site. If traffic delays the truck, if the drum stops rotating, if the concrete begins to separate, the entire load can be ruined. That's thousands of dollars lost instantly. So, to keep everything flowing smoothly, mixer trucks are scheduled in tight rotation. One unloading, another arriving, several more lining up behind. It's a concrete conveyor belt on wheels, and once those trucks reach the slipform paver, the most critical moments begin. This is where everything comes together. The slipform paver waits like a giant metal animal, and the mixer truck backs up to feed it. Concrete slides down the chute into the paver's receiving hopper. The timing must be perfect. If the paver moves too far ahead without enough concrete, the surface becomes uneven. If the concrete arrives too quickly, it piles up and spills, but once the flow stabilizes, the machine transforms into a moving factory. Inside the paver, an auger spreads the concrete evenly across the full width of the future road. Vibrators consolidate the mix, shaking out air pockets and ensuring a dense structure. Spauta. Then the slipform mold at the bottom shapes the pavement to the exact thickness and width, all while moving forward continuously. Laser sensors and GPS systems guide the entire machine. If the road needs a slight curve, the paver adjusts. If the elevation changes, the machine raises or lowers itself automatically. The digital controls ensure the finished surface is as flat and aligned as possible. And hidden inside the machine is something even more important: the dowel bar inserter. These steel bars must sit at precise depths and positions to transfer loads between slabs and prevent future cracks. In older construction methods, workers had to place them by hand. Modern machines insert them automatically without stopping, a huge leap in quality. The continuous slipform method eliminates cold joints, the weak spots where separate concrete pours meet. Instead, the entire slab forms as one seamless structure, stronger, smoother, and far more durable. Machines of this size and sophistication aren't cheap. Depending on their configuration, they can cost anywhere from $120,000 to more than $300,000. But their precision and speed make them indispensable for modern highway construction. By the time the paver reaches the end of a segment, an entire section of roadway lies completed behind it, but still fragile. Because fresh concrete needs protection, or all that precision could go to waste. Fresh concrete might look solid, but the first few hours are critical. If moisture escapes too quickly, the surface can crack. If the temperature shifts suddenly, the internal structure can weaken. So the moment the slipform paver moves on, workers spray the surface with a curing compound, a special liquid that forms a thin film to trap moisture inside the concrete. A few hours later, once the concrete is firm enough to walk on, crews begin sawing expansion joints. These cuts allow the slabs to expand and contract with temperature changes without cracking. The timing must be precise. Cut too early and the edges crumble. Cut too late and the concrete may have already cracked internally. After the joints are cut, workers clean them thoroughly and inject a flexible sealant, often silicone, polyurethane, or bitumen. This sealant blocks water from entering the gaps. Because if water seeps in, freezes, and expands, it can destroy the pavement from below. Next, the road undergoes several days of controlled curing. Signs and barricades prevent any vehicles from entering. Engineers run compressive strength tests, measure flatness with lasers, and check uniformity across the entire surface. Only when the concrete reaches the required strength, usually after about a week, is the road open to traffic. But that entire process, as high-tech as it is far from universal. In many parts of the world, roads are still built the old-fashioned way. In regions where budgets are tight and machinery is rare, road construction becomes a people-powered operation. Instead of a slipform paver, dozens of workers line up with shovels, rakes, and long screed boards. Mixer trucks dump wet concrete directly onto the ground. Workers sprint to spread it before it begins to set. Handheld vibrators are used to remove air pockets, but coverage is rarely uniform. Surface leveling is done by experience, not sensors. The result depends heavily on the skill and exhaustion level of the crew. In countries like Peru and many parts of Southeast Asia, this method is still common. It's not that engineers don't want modern machines, it's that remote locations, limited budgets, and logistical challenges make automation difficult. Because of this, the quality varies widely. Without laser leveling or automated compaction, the surface may develop dips or uneven spots. Expansion joints might not be spaced properly. Concrete consistency can differ from batch to batch. But while some countries are held back by limited access to high-tech machinery, Others push the limits of road construction in the most extreme environments imaginable. And nowhere is that more dramatic than China's projects deep inside the Taklamakan Desert. From the precisely engineered concrete highways of the United States to the labor-intensive construction in developing regions to the extreme desert projects in China, roads tell a story that most people never notice. They reflect a country's technology, its resources, its climate, and even its priorities. The next time you're driving, you're not just moving across asphalt or concrete. You're traveling over a structure that took massive planning, huge machinery, advanced chemistry, and hundreds of workers to create. A structure designed to survive decades of heat, traffic, storms, and stress. Roads might look simple, but they're one of humanity's most underrated engineering achievements, and one of the most essential. And as construction technology continues to evolve, who knows what the next generation of highways will look like?